So we have now come to seismic reflection, which is the most important aspect of geophysical methods for oil exploration. When a seismic wave traveling through the earth encounters an interface between two materials, as here, between two materials, with different acoustic impedances, some of the wave energy will reflect off the interface and some will refract through the interface. The seismic reflection technique consists of generating seismic wave and measuring the time taken for the waves to travel from the source, reflect off an interface, and be detected by an array of receivers at the surface. As you can see from this figure, this is a seismic wave and this is its reflection, right? So this is another seismic wave, which is its reflection here. This is another seismic wave, so its reflection is like this. So these are all reflected waves. The seismic reflection technique, as I was mentioning, consists of generating seismic waves and measuring the time for the waves to travel from the source, reflect off the interface, and be detected by an array of receivers at the surface. Now, if you know the travel times from the source to various receivers, if you know the time which is taken up for the wave to travel from the source to the receiver after being reflected, if you know the velocity and the time, the path waves of the waves can then be reconstructed so as to build an image of the subsurface. On land, the typical receiver used is a small portable instrument which is known as a geophone, which converts ground motion into an analog electrical signal. In water, hydrophones are used, which convert pressure changes into electrical signals. Each receiver's response to a single shot is known as a trace and is recorded onto a data storage device, after which the shot location is moved to continue the processing and repeat it. Now, as I mentioned earlier, when a seismic wave encounters a boundary between two materials with different acoustic impedances, some of the energy of the wave will be reflected at the boundary, while some of the energy will be transmitted through the boundary by refraction. Now, the amplitude of the reflected wave is predicted by the seismic reflection coefficient R, which is dependent on the impedance contrast between the two materials. For a wave that hits the boundary at normal incidence, that is perpendicularly, the expression for the reflection coefficient is simply R equals Z2 minus Z1 upon Z2 plus Z1, where Z1 and Z2 are the impedances or the acoustic impedances of the first and second medium. By observing the strength of the reflectors, the changes in the seismic impedances can be inferred. In turn, this information is used to infer changes in the properties of the rocks at the interface, such as density and elastic modulus. The time it takes for a reflection from a particular boundary to arrive at the geophone is called the travel time. If the seismic wave velocity in the rock is known, then the travel time may be used to estimate the depth to the reflector. For a simple vertically traveling wave, the travel time from the surface to the reflector and back is known as the two-way time and is given by the formula TWT equals 2 into d by v, where d is the depth of the reflector and v is the velocity of the seismic wave within the formation. The actual vertical depth to the formation can be calculated from this formula. A series of apparently related reflections on several seismic seismograms is often referred to as a reflection event. By correlating reflection events, a geoscientist can create a cross-section of the geologic structure that generated the reflections. Interpretation of large surveys is usually carried out with programs using high-end three-dimensional computer graphics. Now this is an interpreted seismic section showing the different interpreted layers here, and so on. This is the corresponding geological cross-section of the same. This here is a 3D interpreted seismic section in 3 dimensions. We will discuss methods by which the reflections from a particular reflector can be accentuated. We can accentuate the reflections by the common depth point method. To understand the common depth point method of accentuating seismic reflections, we need to understand seismic reflection patterns from a single fold split spread data first. Now, this cartoon shows a single fold split spread data arrangement. The seismic section alongside is that of a single shot split spread seismic survey two-way time section. The shot points are depicted at the surface as red dots. Continuous reflections start building up at a shallow depth, and they continue thereafter, depicting the depositional layers. The faults are interpreted in yellow. A shallow structure showing a very gentle seismic reversal is marked in yellow here. This structure seems to continue deeper down, but is dislocated by a fault. At point A, just below the crest of the shallow structure, the deeper reflectors seem to be going downward. Also, if we track some reflectors like this one, we see that for a particular reflector, its strength seems to be varying from one end to the other end. This could be due to noise or due to stratigraphic variations. Quite evidently, the geoscientific information from the section that can be gleaned is only partial, as the resolution of the section is poor. To improve the resolution of the seismic sections, we use the common depth point method, wherein the same depth point is imaged by a number of source reflection pairs in succession. The subsequent presentation discusses the CDP method of data gathering and data enhancement in greater detail. We will discuss the common depth point method further. Now, this is a source receiver arrangement where you have a source on the ground, a number of receivers 1, 2, 3, 4, 5, and 6, and these are the reflection points 1, 2, 3, 4, 5, and 6. The point to note here is the subsurface information returned to the surface is limited to one reflection from each point on the reflector. As you can see, from point 1, there is only one reflection. From point 2 is the next reflection. From point 3 is the next one, and so on. Each reflection is marked in different color. Obviously, if there could be additional recordings of each individual point, here, here, and here, a clearer picture could emerge. The common depth point method of data acquisition improves the signal-to-noise ratio by acquiring more observations of the same point and then adding them up together. Now I'll try to explain this CDP further by means of an animation. In this case, this is the ground, this is our reflector, And this is a seismic source, which could be explosion or vibration. When this explosive is blasted, we get an array of waves like this. Here, the waves are reflected at points 1, 2, 3, 4, 5, and 6 on the reflector, and each is reflected back as a single reflection from a single point. See here, a single reflection from point 1, a single reflection from point 2, and so on. They are received by receivers 1, 2, 3, 4, 5, 6. If now, in the next step, we move our source to the receiver point 1 and blast it, we get another array of waves marked in yellow. Now what happens due to this new array of waves? If you see it carefully, you'll find that at these points, at receiver 3, 4, 5, and 6, we get two reflection waves at the same point, at the common depth point. And then in the next step, the source is moved to the next short point and blasted. When it is blasted, you get a third array of waves like this. And what happens due to this? We get enhanced multiple reflections from the same point, from the same common depth point. As from here we get 3 reflections, from here we get 3 reflections, here we get 2, here we get 2, and so on. The maximum number of reflections which can occur from a particular point is known as the foldage of the survey. So we can have a 6-fold CDP survey, or a 12-fold one, or a 24-fold one, 48-fold, 96-fold, 128-fold, and so on. Recorded signals are subject to significant amounts of signal processing before they can be interpreted. The more complex the geology of the area under study, the more sophisticated are the techniques required to remove noise and increase the resolution. Modern seismic reflection surveys contain large amount of data and so require large amounts of computer processing, and these are often performed on supercomputers or computer clusters. There are 3 primary steps in processing seismic data: deconvolution, stacking, and migration, in the usual order of their application. This is the usual order: deconvolution, stacking, and migration. All processing techniques come under these 3 heads. These 3 steps, deconvolution, stacking, and migration, can be represented on 3 coordinate axes. If you see this cube here, deconvolution is on the z-axis, offset is on the x-axis, y-axis, and migration is on the x-axis. The deconvolution acts on the time axis, and its job is to increase the temporal resolution. Stacking compresses the data volume in the offset direction and yields the plane of the stacked section. Now, offset is the distance between the source and the receiver. There is a delay in the arrival of seismic waves at successive receivers, which needs to be corrected. Migration then moves the dipping events to their true subsurface positions and collapses diffractions. So, what does migration do? It increases lateral resolution. Deconvolution and stacking are highly complex processing techniques and require large amounts of processing. We shall not discuss them in detail here. We shall, however, touch upon certain aspects of migration and migration techniques in the succeeding slides. I will touch upon some aspects of deconvolution here. This is an image of the Copernicus crater on the moon. The photo shows structures within the crater, but they appear to be blurred. Now, this is the same crater, the same image after deconvolution. Deconvolution improves the signal to noise ratio, resulting in a sharper image. And now, the structures within the crater are visible. The same principle is applied to seismic data. This is an image of an unprocessed seismic section. When the seismic waves pass through the earth, they are disturbed by the inherent heterogeneity that is encountered. The resulting image is blurred and the reflectors are not clearly defined. This can lead to major errors in seismic interpretation. This is the same image after deconvolution. The deconvolution again improves the signal to noise ratio and generates a sharper image. The seismic reflectors are now more clearly visible and their continuity is better defined. We will discuss stacking. This figure here is a split spread common midpoint gallery. Now you can see that this is the common midpoint and these are the sources 1, 2 and 3 and these are the receivers 1, 2 and 3. These recorded traces are corrected for move out. Move out is the distance between the source and the receiver. This is the move out for 1. This is the move out for source receiver set 2. This is the move out for source receiver set 3. Now the signal from the receiver 1 arrives first, followed by signals from source 2 and 3. So the theoretical trajectory of the signals received is hyperbolic. Now this has to be corrected by applying move-out correction algorithms. Figure C, this one, shows the trajectory of the signals after the move-out correction is applied. These are now properly aligned along a straight line. These signals are then summed, resulting in an enhanced reflection. Let us talk about migrate. Some pitfalls of unmigrated sections. In unmigrated sections, the time section reflectors do not reflect the true subsurface geometry. Let us take a look at this figure here. This is the seafloor and what happens because of this depression. A syncline or depression on the seafloor is imaged as a bow in a bow tie effect in a time section. The top figure shows a sharp synclining feature on the seafloor. The figure below shows the bow tie effect at the formation's reflecting surface. This is the second pitfall of migration. Now, the addition of diffractions from the ends of reflectors result in a very complex time section. Now, this figure shows a properly migrated geological section in time. It consists of 3 reflectors, reflector 1, reflector 2, and reflector 3. The figure B shows the corresponding unmigrated time section. This complex false reflector pattern is due to the diffractions produced by reflector 2, which is of greater length than either 1 or 3. Now, this is the third case. In this case, a dipping reflector is shallower in the seismic section than the actual reflector. The actual reflector is deeper than what is seen on the seismic. This is a comparison of an unmigrated and a migrated seismic section. The migrated seismic section shows much greater detail, it's quite obvious, than the migrated section, than the unmigrated section. This is a depth converted time section. We had already covered these topics earlier in an earlier video. In this video, we have covered some aspects of geophysics like data acquisition, data processing, and data interpretation. One major aspect of geophysics, which is related to wells, that is formation evaluation, will be covered at a later stage. And also, we shall be covering reservoir engineering. I've spent considerable time and effort to put together this video. If you like this video, please press the like button. That will give me more encouragement to produce more such videos. Thank you so much for watching, for listening so attentively. Thank you once again.